Good day, everyone. I am happy to share our research entitled Mathematical Modeling and Monte Carlo Simulation of Negative Emission Technology Portfolios. My name is Maria Victoria Migos Sumagang from the University of the Philippines, Los Baños, and my co-authors are Professor Raymond Tan and Professor Kathleen Aviso from De La Salle University. The presentation is divided into 5 parts, and we will begin with the introduction. There is undeniable scientific evidence that human-made emissions are causing global warming. Modeled pathways show that the emissions need to peak by 2025 and reach net zero emissions by 2050. Without our action, global warming will cause extreme weather events that intensify as the temperatures increase. And we have seen the increasing frequency of these extreme weather events all over the world, such as flooding and super typhoons. Aside from the traditional decarbonization options like renewable energy, etc., negative emission technologies that remove carbon dioxide from the atmosphere are now needed to biophysically and economically achieve net zero emissions. However, these nets will consume resources that compete with other societal priorities. Thus, net portfolios that recommend a technology mix of individual nets at smaller scales are preferred to lessen the environmental and social impact. These concerns present the need for integrated net portfolios that optimize resource consumption, and process integration can help with that. Process integration is a subfield of process systems engineering that deals with the integration of whole processes to reduce resource consumption and emissions. And among the techniques used in process integration, mathematical programming can handle the different tasks such as simulation, optimization, design, selection, and ranking of net portfolios. Mathematical programming has been used in optimizing net portfolios under multiple resource constraints. But for industrial scale applications, variations in the resource availability is present. For example, variations in the fertilizer and energy supply in small scale applications should be considered to ensure the robustness of these solutions. Robustness means the ability to withstand varying conditions to ensure the continuous operation of these technologies. And one way to address this is to generate suboptimal and optimal and suboptimal solutions because this optimum solution is not enough. The next step is subjecting these solutions to robustness checking. This is based from this concept, which is the optimum is not enough. The decision maker has to check the suboptimal solutions as well. And this two-step approach has been demonstrated in biochar and decarbonization networks, but have not yet been applied to net portfolios. Therefore, the knowledge gaps identified are first, there is a lack of studies on net portfolio optimization considering resource constraints. Second is there are a lack of studies evaluating the robustness of optimized net portfolios. And to address these knowledge gaps, this study first develops a mathematical programming model for optimizing net portfolios. And to illustrate the model in a case study, the second objective is to apply the two-step approach, the generation of optimal and suboptimal solutions, then robustness checking, on net portfolio selection. So this study contributes to the development and analysis of optimum net portfolios for emissions reduction planning. Moving on to the problem statement and the overview of the methodology, the problem is as follows. Given a set of nets and a set of resources, their specific constraints, and given other model inputs and targets, the problem is to build the optimization model that minimizes the cost of the nets portfolio while meeting the other constraints. And using this model, the next objective is to to generate optimal and suboptimal solutions, and then subjecting these solutions to Monte Carlo simulation by varying the resource constraints. And the last step is analyzing the robustness of the solutions to recommend the best portfolio among the generated solutions. Moving on to the methodology, the optimization model is structured as shown. The objective function is to minimize the total cost of a net portfolio. And this is subject to a target negative emissions capacity. And the resource and capacity constraints also have to be met. After developing the model, the next step is solving and generating the optimal and suboptimal solutions. This is done through integer cut constraints, following the procedure by Vol et al. Alternatively, this can be done in using the commercial solver. And for Lingo, which is the solver used in the study, this is done by setting the k-best solutions under the integer solver tab of the preferences. The next step is subjecting the solutions to Monte Carlo simulation. So Monte Carlo simulation is a mathematical technique that rely on repeated random sampling to obtain numerical results. And the keyword here is randomness because we want to deal with the stochastic uncertainties in the resource availability. And we do this by first getting the probability distributions of the inputs, in this case, the probability distribution of the resource constraints. Now, next is to generate a random sample input following the probability distribution. And the model is solved using the sample input. The results are recorded. The procedure is repeated until the number of simulations reach a large number, in this case, 1,000. The probability of network failure are calculated for each solution. And we do this by getting the percentage of um, number of failed solutions divided by the total number of simulations specific to a resource. To get the overall probability of failure, we consider the failures in all of the resources. And the last step is recommending the most robust solution with the lowest probability of failure but acceptable cost. Moving on to the case study, 6 terrestrial nets are considered, and their potential environmental footprints and costs are obtained from the literature. 5 resources are constrained in this study, but for the resource availability, only water, renewable energy, nitrogen, and phosphorus are investigated for variations. Since the available land is usually not subject to variations, but for water, renewable energy, nitrogen, and phosphorus, they they can be subject to variations in availability. For example, variations in the supply of the fertilizer and the energy supply. The standard deviations were estimated based on the annual consumption of the resources in a country. And out of the solutions, 4 solutions are selected for analysis, which are ranks 1, 2, 4, and 5. Rank 3 was skipped because it has a very similar configuration with another solution that is already included in the analysis. And the figures show the different configurations of the optimal and suboptimal solutions. A green color means the net is activated in the portfolio, and the gray color means the net is deactivated. So the solutions have different technology mixes of the nets. For example, solution rank 1 or the optimal solution Here, all nets are all nets are activated. But for the rest of the solutions, like for example, solution 4, BCCS and biochar are deactivated. So in terms of cost, let's look at the table. Obviously, the optimal solution has the lowest cost because the objective is to minimize the cost. Well, the rest of the solutions have increasing costs. Looking at the probability of failure, the optimal solution has the highest probability of overall probability of failure at 48.5%, while the rest of the um probability of failure for the rest of the solutions decrease. And we can see that uh, the probability of failure is mostly attributed to nitrogen. So how do we explain this? So from the figures, we can see that the suboptimal solutions, rank 2, 4, and 5, have lesser allocation for the biologically based nets like BECCS, biochar, and SES. And decreasing the allocation of these biological based nets, which require nitrogen, increases the robustness of the portfolio. But it implies that we have to increase the allocation of direct air carbon capture and storage, which is the uh, currently most expensive net. So, since the probability of failure depends on whether the solution is nitrogen intensive, the decision maker may opt to find a balance between the nitrogen requirement and while considering the impact on the cost. For the conclusions, this study met two objectives. The first is the development of a mathematical programming model for optimizing net portfolios and the illustration of this model in a case study. The second objective is the application of the two-step approach, which is the generation of optimal and suboptimal solutions, then subjecting to Monte Carlo simulation for robustness checking on net portfolio selection. So doing this two-step approach does not only give us the optimal solution, but a compromising solution that is more robust at the expense of cost. This work supports the development of decision support models using nets for emissions reduction planning. For future work, I recommend considering multi-periods and exploring stochastic optimization techniques. If you are interested in the other optimization and decision support models for deploying nets, I would like to invite you to view our review paper using the QR code or the link. It's open access. Thank you very much. Comments and questions are welcome, or you may also contact me using this email address.